Welcome to Lab 5. In Lab 5 we're going to cover composite data types, and by composite data types we generally mean things that combine together lots of things into one package. So in particular we're going to look at a new concept called a struct and how we can create new types that are all the various types you've seen so far but packaged together into one structure, in which we call a struct. So before we go into the setup and how to start solving the task for this particular lab, first I want to cover some basic concepts that you need to know, like what structs are, how pointers to structs work, and how when you allocate memory, how you have to be a bit careful in how you allocate memory and how you access the memory when you have a struct type. So before we go into the setup and the requirements for this task, let's just look at those basic concepts. So let's take a look at this sample program. It has, it's a very basic sort of main function which has some variables defined, and the first variable is defined on line 6 here is a char array which is assigned to this string hello. And this is exactly the same as doing this assignment, which is char c is assigned to hello and a 0 for a null terminated string. And now from line 7 to line 11 we can see that we have defined a struct. A struct is simply a way to package together all the basic types we've seen so far. So any of the basic types we have seen, like integers, doubles, floats, characters, bytes, whatever type you want, you can put into a struct and package them together into one. So this struct, for example, contains two integers, and we're going to call these two integers by some name. So a name will help us define which integer we're talking about. So this is an int a and an int b, and then there's an array of characters. In this case we have to give the length exactly, because C needs to know how much space to allocate for this struct. And it's just going to allocate this struct as a one contiguous piece of memory. In this case, it's going to assign a portion of stack memory for this variable. And we've said this x is a variable of this type struct, which has exactly these fields. So in this case I can assign x dot a to 10. So this is assigning the value 10 to the first element a of this struct. X dot b is the second element b of this struct here to 20. And then I have a for loop that assigns x dot ci. So this is each element in the array I have in this struct is assigned to ci, which is the array I declared here. And then I'm just printing out the values of xa, xb, and xc, and when I print out xc I'm printing it out as a string because that's what a string is. It's just a character array that is null terminated. So we are guaranteed that that's true in this case, as I copied the entire string ci into x.ci, right? So I'm copying all of the contents of this array into this array, and so when I run this, you can see that I get 10, 20, and hello, which is what I expected. I assigned the first element of the struct to 10, the second element of the struct 20, and the third element to the string hello. Now let's take a look at a slightly modified version of the same program. So it starts out the same. We have the same character string defined as before. We have the same struct as before. So it still has two integers, a and b, and a character array defined as the variable x. And then right after that I have defined, it's exactly the same structure, and I've created a new variable of that structure type. Notice that in order to make another variable of the same type, I had to write down the whole structure again. And a bit later I'll show you how we can get around typing all of the structs again and again by just declaring it once as a type. But for now, let's just assume that we typed in this entire structure again and we assigned it to y, and this time I'm directly assigning it to a value. So if you remember before, I had x.a is equal to 20, x.b equals 20, and then I copied over the character array into this array for c. And this time what I'm doing is, instead of x.a equals 10, I'm just assigning y.a to be 10 using this initialization syntax. Let's see, lets me initialize this variable by just giving the values. So I say 10, 20, hello. And now I'm printing out at the end both the values of the struct x and the components of the struct for y. So when I compile this, you can see that they print out exactly the same values. So initializing it or assigning it has the same effect. So one canonical way to use the struct type is to first declare it as a type. So we do that by using a typedef declaration. So this typedef literally says we want to define a new type. So it's typedef, and the typedef is struct. This is the same struct that we've been using for the last couple examples. So there's a integer a, integer b, and a character array that is 6 characters long. And now instead of a variable, I'm actually going to declare a new type. So what we've done is created a new type, which is a new type, just like int is a type, or character is a type, or double is a type. So we've created a new type, and it's a type just for us. All of the programs that use this typedef can now access a new type called x_t. By definition, we add an underscore t. Sorry, not by definition. By convention, we add an underscore t. There's nothing special about having an underscore t that makes it a type. What makes it a type is by using typedef. So usually you'll see different types with the underscore t. That's if somebody defines a type, they usually use underscore t at the end, and that's just a convention just to tell you that that's a type that was declared. So now when I want to use it as a type, I use it exactly like I would any other type. So this one is a character array, right? So I have a C, and then I have this array here. So just like I use character as a type, I use x_t as a type, and I define a new variable x of that type. And in the same way, I have x_t used again. So remember, in the previous example, I had to type out the whole struct twice, and now I don't need to. I can just use the same type and declare a new variable of that type. And I can even initialize it as I did before, and everything else works the same way. So when I compile this file and I print, so everything works the same. There's nothing different about it. It's just that instead of using an explicit struct, I'm now using a typedef, and that's generally how we use structs. Very rarely we might put in a struct because we don't want to use it again, but when we want to reuse a struct definition, we create a new type and then create variables of that new type that we just declared of this struct type. So now let's take a look at how to allocate a struct on the heap rather than on the stack, which we've been doing so far. So in this case, we're going to define the struct type as before. So we have a typedef, and it defines a new type x_t. But this time, instead of allocating it as a local variable on the stack, we're going to actually try to get a pointer by allocating the memory on the heap, which is what we get when we use malloc. In this case, you would get a pointer which is of the size of this struct, so the size of this type x_t, and we ask for a space that's big enough to assign values to this the values of this struct. So when I allocate memory, I now have space for 2 integers followed by a character pointer. So one thing I've changed here is this is a character pointer now rather than a static array. So in this case I get a pointer which is allocated on the heap, and now I can manipulate x. So the first thing I do is I check whether x is equal to null. Null is just another way to say whether x is 0. So when malloc fails, it cannot find memory, it will return a 0 or a null pointer. We can check if x is equal to null. If it is null, we print out the error that was returned using p-error, and we return 1, which is a failure back to the shell. And now, whenever we had a pointer, we used to dereference it if you want to put something in it. So that's exactly what we're doing in this notation here. There's a dereference of x, so star x, which says give me the struct that's in this memory location, and that's interpreted as a struct, and I put brackets around it because I want to first dereference it and then get the a field out of this struct. So we first dereference it so that it becomes a struct, and then we assign to the first field dot a is assigning to a the value 10. And then the same way you assign to value b, assign to b the value 20, and to c we do another malloc because it's a char pointer, as you can see here. Since it's a char pointer, we're going to assign a new allocated memory, and it's going to be the length of the string I'm going to copy into it, which is this static string here, hello. So it's taking the length of that string times the size of characters and creating new space for it. And then I'm going to use memcopy, which is just a function that copies these number of bytes. So the strlen of c, so it should be strlen of c times size of character is the number of bytes, and it's going to copy it from the source, which is c, into the, we dereference x first, and then we get the c out of it, right? So, and then I just print out the different components, dereference x, take the a component, dereference x, take the b component, dereference x, take the c component, print it out as a string. As you can see, it's pretty tedious to write down dereference x dot a, dereference x dot b, and so on. So C has a shorthand, which is called pointer indirection. So instead you can put this arrow notation. It's exactly the same as this, but it's just a extra notation that C gives you to avoid having you type this over and over again. So as you can see, when we compile this and you run it, it has the same effect as what it had before, but this time the space that was used was allocated on the heap, and you can also see that there was no difference whether I use this dereference notation or whether I use this pointer, this arrow, indirection arrow notation. They both have the same effect. It prints out exactly the same thing. So let's look at an example of where you might find something like a struct very useful to organize your code and to make it easy to read, and also to avoid bugs where different parts of your data get confused. So let's just look at the header file that you were using called imageops.h for the previous lab. And in this case, every time we pass in an image, it was an array of pixels. Each pixel was of type uint8_t. And every time we pass a image of this pixel array into a function, We also pass the number of columns, so the width and the height in number of rows. So we always used to pass the image, the width, and the height. All the functions, as you can see, will contain this. So every single function will have the image array, the number of columns, and the number of rows. And it would be nice if we could encapsulate all of these into one unit. So as you can see here, and this version of the image image ops, what I've done is created a struct that represents 3 different pieces of information, 3 pieces of data. The first is the width of the image, which we assign to this unsigned int variable w, and the height of the image, which is assigned to this unsigned int variable h, and then a pointer, which we will allocate later to a, so it's going to be an array. Since it's a pointer, it's going to be an array when I allocate it, and it's going to contain enough space for all the pixels for image of this width and this height. So this variable is given the name pixels, and so I can put each of the colors, so each color will be a uint8 underscore t. I can assign each element of this array to one of these colors depending on the xy coordinate of that color pixel. And we assign this typedef to a new type called image underscore t. And every time we want to now pass an image, we don't have to pass the pixels and the height and the width as separate things. We can just pass them all together using this image type img underscore t. So when I want to show an image, I just pass it an image t pointer, and then I can dereference the pixels using the pointer, the indirection arrow point. So as an image, and look at the pixels inside the pointer image, and then I look at w and h also inside this pointer image. So I'm taking this pointer image and I'm looking inside the pointer for the pixels part of this structure, and then I'm returning that when I do this. So when I want to create an image, I still have to pass it the width and the height and maybe the default color. And what I do is I malloc some space that's big enough for an image, so the size of image t, and that's going to give me a space which is going to be as big as this struct. So it's going to have 2 integers and enough space for a pointer. So notice that in this malloc we haven't yet allocated any space for the pixels yet. So we're going to assert that the image was actually given some space, so malloc did succeed. And now I can assign, I have 2 integers, the width and the height, and I can assign them. But before I assign any pixels, I have to first allocate space for it. So I look at the number of bytes I need for the pixels. It's the width times height times the size of each pixel, which is uint8 underscore t. So that's the total amount of information, the total amount of space I need to allocate for all the pixels. And then I do a malloc for the pixels. So notice that I have done 2 mallocs. So first malloc was a malloc for this struct here, and the second malloc, which is here, is to allocate space for this pointer, which is the pixels of the image. And then I'll make sure that that allocation succeeded. And then I can do a memset, which is an operation that takes a pointer and it takes a value and then a number and just assigns the value color to all of the So these number of locations that's pointed to by this pointer here. So it's going to simply copy this number color into all the bytes in this pixel array, and then I just return this as a newly created image. And then just to show you how we can use this representation to actually draw something, here's an example function called image line, which just draws a line, and it takes an image, a pointer to something of image type. And remember that each image type has a height and a width, and it also has the pixels associated with this image, enough space for it. And what is this function is doing is taking a start coordinate x1, y1 and an end coordinate x2, y2 and a color, and it's just going to draw a line from x1, y1 to x2, y2 of that color. And it's not really important for the sake of this lab exactly what algorithm it's using. It's pretty simple, so you gotta look at this part first. It's just dividing it up. It takes a midpoint of the x, so it first finds a midpoint, the halfway point between x1, x2, and it finds a midway point between y1 and y2, and then it splits up the line into these two parts at the midpoint, and it recursively calls itself. So image line is calling itself, and it says, okay, draw me the first half of the line, and then this one says draw me the second half of the line, and it does this recursively until it gets to a single point where x1 minus x2 is less than 2, or and y1 minus y2 is less than 2. So basically every point that it finds, then it just assigns that trivial line of 1 pixel with a color. So this is how using a recursive function can make something fairly complicated, reduced down to the base case, and the recursive case is sort of feeding you all the pixels you need to draw. And then finally we just have a main where you create image. It gives you back an image pointer, image t pointer, and then I draw a few different lines just to show a demo of the image line. And so when you run this, you can see the image. So as you can see, it just draws these 3 lines in these different colors. So just to show you the demo, it's not really relevant for the struct and pointer discussion we're having, but just to show you that it runs. Let's go back and look at the source code for the image drawing program, which uses the image type struct, the image underscore t. And notice that we have a pointer to an image type. We also have inside this structure another pointer, which is pointing to a memory location that contains all the pixels. So when we deal with structures like this, we have a pointer for the structure itself, and we have a pointer for the pixels, or whatever is and there might be any number of pointers inside the structures. In this case, this is a pointer pointing to all the pixels. You have to be extra careful how we make copies of such structures, because we might end up making a shallow copy which copies the contents of the structure but doesn't copy what's inside this pointer, because this pointer, remember, a pointer is just a memory location, so this just pixels is just pointing to a memory location. If you say that you made a copy, but in fact the copy just contains a copy of this pointer, now you have 2 pointers pointing to the same location. So let's look at an example of doing a shallow copy like this. So first let me remind you that image create takes a width and a height and an initial color. It does a malloc for the structure, image type, and then it does another malloc for the pixels and assigns it to image, the pixels that's inside the image pointer, and it then sets those pixels to the color. Okay, and image destroy is a function that takes an image pointer, a pointer to image type, image t, and it does a free of the pixels. So whenever you have a malloc, you should have an associated free, otherwise you have a memory leak. So image destroy here is going to take the memory associated with all the pixels and free it, and then take the image, the pointer image which is pointing to a struct of type image t, and free that. So notice that there are two mallocs, this malloc and this malloc, and now there are two frees, this free and this free. Okay, so let's look. So keep in mind that we have a create that does two mallocs, a destroy that does two frees. Now let's look at the main function. Now in the main function, so it's a very stripped down version of the one I showed you earlier. All it's doing is creating a new image called image1, and it's using image create, which returns a pointer. So it's assigning this to an image t pointer, and so image1 is a pointer to something which is this struct image t type. And now I'm creating a new variable image2 of the same pointer type, and I'm just assigning it the value of image1. So notice that the left hand side of this equal to has an image t pointer, the right hand side also has an image t pointer, right? So therefore this is a valid assignment. Now when I assign this, what I have now is two pointers pointing to the same location. So notice that we did not do a new alloc for image2. So now let's just print out the values in image2. So what I'm doing here is I'm looking at the number of bytes that are in the pixels for image2 and image1, and I'm just writing a printf statement that prints out the width and the height and a random pixel from all the pixels. So just it picks one random pixel and prints that out. So it's doing that by creating an index that is a random number mod by the number of bytes, so it doesn't overflow the array. And then I destroy image1 and I return. So let's take a look at how this runs. So notice that it shows the width and the height and a random pixel. So everything seems to work just fine. Now let's look at this function again, and now let's see what happens if I take this image2 and I destroy image2. So when I do that, as you can see, it's going to create a segmentation fault because I'm freeing the memory twice. I did not actually make a copy of that memory, so I don't own it. So because of that, I've created a bug. When I do an image destroy for image2, it's not going to be a valid operation. It's going to free something I've already freed before. So this image2 is not a real copy of image1. So let's look at how we can make a real copy. A real copy is often called a deep copy because what it's doing is copying not just the top level structure, but also copying the inside pointers of that structure. So it doesn't just stop at the top level. You have to copy these, and if this itself was a pointer pointing to a bunch of things that have pointers in them, then you would copy those as well. So deep copy can sometimes involve going deep into a structure, going down different pointers. In this case, there's only it's only one level deep. So we'd only need to do a deep copy of the structure and all the pixels inside it. So let's take a look at how to do that. So in this function now, I'm creating an image1, I just create a new image. Now I still is not a copy of image 1. I just created a new image. In order to make sure that it's a copy, I have to make sure that the width and the height are the same, which I've done by just copying over. Now assume here that there's lots of code in the middle that modifies image 1. So I don't really know that all of the values will be 255. In this case I know it is because I don't have that code, but imagine there's lots of code here that changes, like I drew several lines in this image. Now I want to make a copy of it. So I can't really know what all the pixel values will be in image 1. So I'm just going to set it to 0 as a default value. And then I'm going to look at the size of the image 1 pointer to pixels. So this is the number of bytes is equal to the width times the height times the size of the type of each color. And I'm going to use memcopy, which takes a destination pointer, a source pointer, and the number of bytes to copy. And this memcopy now makes a faithful copy from the image 1 pixels into the image 2 pixels. So now image 2 has the same width, the same height, and all the image pixels are exactly the same. So now when I print it, I can see that it will print out a value, and now I can destroy the second image and it won't give me a segmentation fault. So there you go. It did both of the destroy images here properly without incurring a segmentation fault. So that's how to make a real copy when you're dealing with pointers that can be inside a structure. And so sometimes you might have to do a deep copy that goes inside another pointer and looks at whether that is pointing at things that have pointers in them and so on. So sometimes you have to go really deep, like if you're copying a tree structure or something much more complicated. In this case, it's a fairly simple operation to copy. And in your Lab 5, you'll also have to do a deep copy. And it's also something you have to think about when you do a copy. You have to make sure that you copy all the data that's associated with pointers inside the data structure. One useful thing that you often have to do when you're dealing with memory allocated on the heap is that you might want to change the size of it. So let's look at this example. Here are just two strings I've set up. One is hello, and this is a very long string. I've allocated some memory on the heap using malloc. And for the first one, I've used the length of the first string. So in this case, it would give me a size of 6. There's 5 for the characters plus the null at the end of the string. And now I'm using malloc, and I get space that is enough space for 6 characters, and each is of a size of the character, so basically 6 bytes. And I use a string copy function, which is defined in string.h, and I copy the contents of the string h into the newly allocated x, and I print it out. Now if I wanted to change the size of this, I could just free x and allocate a new pointer, but the system allows us to try and stretch this memory that's been allocated if possible. So if there is some extra space available in memory that is contiguous with the pointer that was allocated to you using malloc, then you can use realloc to try and get some extra space added on at the end of your current pointer. Of course, that's not always possible. So realloc make sure that if there is no space, if you're asking for too much space and there isn't enough to add on to the end of the space that is pointed to by the current pointer. So let's say x is pointing to a memory location and you ask for 6 bytes, and now you're asking for 20 bytes. it might look and see if there was additional space that it can say, okay, now the pointer points to 20 bytes. And the pointer value doesn't change, but the length allocated to it changes. If it cannot find that extra space, then what it does, it allocates a new space on the heap, somewhere completely different, and then it copies the old values, the old whatever 6 values there were, into the new space, and the rest of it puts 0 values, and then it returns, the realloc returns a new pointer, the new pointer location. So sometimes it's returning the same pointer that gets passed into realloc, sometimes it's returning a new pointer. So we just assign whatever it returns back to the old pointer x. So we don't really care if it changes or not, it handles that situation for us. And now I copy the longest string into x, because now it's allocated some more space, and I print it out. So I always free this pointer. So notice that I did not allocate 2 pointers, I just allocated 1 pointer, and then I resized it, and when I print this, when I run this demo, you can see it prints a shorter string and then it prints a longer string. Let's finish up by looking at the setup for Lab 5, and it's pretty straightforward. As before, you go to your repository, make a directory for your current lab, which is 5, get this one file that you need to get. The instructions are on the web page. And now let's look at this file. It's very similar to one of the labs you had before. You basically have to implement each of these functions, and each task is mentioned clearly in the header file. So obviously you're not modifying the header file at all. What you're doing is creating a new file, and the new file is, has to be called intarray.c. Now let's examine one thing that appears in intr.h that you may not have seen before. The first part you've seen before, it is typedef. Just like you make a new type for a struct, this is using a typedef to create a new type. But instead of a structure type, instead of a struct type, like you can see here, this is called an enum type, which is short for enumerate. And it's basically a list of, by convention, these are capitalized. They don't have to be, but it's just because they are constants, they are by convention capitalized in C. And these are different values. So intr OK in an enumerate structure is assigned the value 0. Intr bad array is assigned the value 1, and so on. This is bad index, it's assigned 0 and 2, 3, 4, and so on. So it is assigned a number, but you actually don't care what that number is. What you care about is the fact that you have packaged these numbers together, these variables. Well, they are not exactly variables because you can't assign anything to them, right? They're constants. So these constants are grouped together using an enumerate type, and they're given a type that you can use. So int results t is a type. And what we're going to do in this lab is, for all of the tasks, for many of the tasks, not all of them, but many of the tasks, we want to return a value that tells us whether our function succeeded, in which case it returns an OK. If it was not a good array that you passed in, then it returns a bad array. If it was a bad index, it gives you that result, and so on. So these are basically result values, and there is a small fixed number of them. So we want constants to refer to the results that you can get out of calling functions that you're going to write. So all of the functions you're going to write, some of them return pointers to memory locations, in which case if they fail, they return null. If in other cases they're modifying an array in place, so they're not returning a new array, but they're taking an array as an argument and then returning whether it was able to change that array. And so that's why we need some way of specifying a group of constants. And this is what this enum type does. Enum type lets us package together these constants that we can use in this particular case as return types, as a return type for our functions. So in other cases, you might be able to use enum types for other things, like, for example, you might want to record what state your program is in. It goes from one state to the other. Let's say it's waiting for a result. You might use a constant to specify that. If you are reading a result, you might use a constant to specify that. So there's many ways that you can use a group of constants specified in this way. And enum types are a nice way to package up your constants and then give it a type. And then the nice byproduct of this is that C will do some type checking for you. So if you return something which isn't a valid result, then C will catch that and compile time and tell you that there was an error. So that's one thing you can read up on as well, is enum types, but they're fairly straightforward, and all you're going to use it for in this lab is you have to return these constants as a value. So you can return, if for example your function succeeded, you might return int or OK. So the specifications for each of the functions tell you exactly what you're supposed to do. Finally, let me just say a little bit about testing. It's very important that, as with all of your previous labs, that you test your programs. Don't just rely on the autograder. So here I've created a testing function. I've put it inside a main and in a separate file. So it includes int_r.h, and it will call the functions that you write in int_r.c. So when I compile it, I will compile test.c and int_r.c together. But you can notice that I have written some of the functions that are required by int_r.h. So I have int_r_create of a certain length, and then I use rand, which creates a random value, and I use int_r_set to set a particular index with a certain value. So these are all functions that are defined inside int_r_h, and exactly what they're supposed to do is specified. As you can see here, I check whether the result is OK, whether it returns this value int_r_OK, which is defined in the enum type int_r_results_t, and I print out what was added to what index, and then I also do an int_r_get, so I can visually examine whether what I put into the array is what I get out of the array. So when I compile this, I can compile this with test.c and int_r.c. That creates a file, and then it prints out a bunch of stuff, which prints out random numbers that I put into the array and that I get out of the array. And I can write something that will test whether those numbers were equal and whether it failed in any way. So this is the bare minimum of the testing you should do. You should do a lot more testing of your functions. As you can see, the amount of code in int_r.c may not be a lot, but testing it will require some extra code, and we do expect you to write that.